for the Project 500 submission of stepping through different PWM speeds with a push button and Arduino in assembly. I have a circuit with the oscilloscope attached to my PWM output, the motor sitting high so that way I won't have to intercept it, a visual LED to toggle whenever the push button is pressed to let us know whenever we're in the other PWM states. For the schematic, I have the Atmega 328P chip here in KiCad. All the pins I am not using currently in ports. They're grounded because that is the practice, as if I took this chip off of the Arduino board. So everything else would be grounded technically. I'm not really using the analog stuff, so for simplicity, I have applied a voltage to both the VCCs, but grounded the analog reference pin there. And for my PWM signal, I output on PB0, port B0. This goes to the 293D H bridge, which I get to in a minute. Port B1 is a input port, so I would be reading in on the pin. I have enabled the internal pull-up resistor, so when the push button is active, I'll be reading for lows in the assembly program. Port B2 is an output port that goes to the visual LED attached to a 100 ohm resistor, so that way we can see whenever we step over. Coming back over here, the same VCC I've applied from the Arduino, I have put a jumper cable over to the VCC 1 and 2 pins on the 293D H bridge. On pin 2, I've applied the same 5 volts since that is what I desire to go to my motor. As mentioned before, the PWM signal goes to the enable 1 and 2 pin on pin 1 of the 293 given by the datasheet, or as recommended. I've coupled a capacitor from VCC to the ground here so that way it doesn't have a sharp voltage increase or decline at changes. The coupling capacitors C2 and C3 along the motor itself are to prevent high backwards voltage to prevent smoking the IC out. The motor attached to the output pins 3 and 6 is driven whenever the enable signal is given in the direction of 1A, so from positive to negative back. I've grounded port 7 here so that way when the current comes back it grounds as it should, as opposed to giving it two 5 volt voltages and causing zero current. So next up is the flowchart describing the program that I will show here shortly. First of all, I'll be initializing the instruction location at reset or 0000 in assembly for the AVR. Then I initialize the input-output port directions and initial outputs, so this will be the DDRX, in. I'll be SBIing, CBIing it. For that input resistor, pull-up resistor, I do SBI port B1. Next up, I step into the generate 0% duty cycle where I turn the motor off using CBI, call a delay. This delay is meant to prevent the push button from speeding through and going to this control statement here. I check if the active high switch is actually low. If it's still high, I continue through the 0% duty cycle. Otherwise, I switch to low. I'll skip that R jump and call a 250 millisecond delay and toggle the LED off and on. Once on again, I know I'm in the 40% duty cycle at 250 Hertz. The 250 Hertz through experimentation was the best frequency for my application since it caused the motor to actually react at 40% duty cycle over some time. I load some GPRs with a ratio of on to off. So I have 4 for on and 6 for off. You add these two numbers, you get a 10. So I'll be on for 4/10 of the cycles, causing a 40% width. I set the motor to on. I call the delay and decrement the on GPR. If the on GPR is at 0, I will step through the program again. Otherwise, I'll branch back up and call delay again until it is 0. Following this, I set the motor off and likewise decrement the off GPR, stepping or branching back up. Once that off GPR has reached 0, I will be checking the active high switch again. If the switch has not been pressed, it will return back to this 40% duty cycle and redo everything. Otherwise, it'll switch low, skip that R jump, and call the 250 millisecond delay subroutine again, and generate the 70% duty cycle after stepping through. Likewise, with the 40% duty cycle here, I have the ratio of 7 to 3 for the 70% duty cycle. I still set the motor on, call the on delay, and decrement it as I'm supposed to. Set the motor off, call the off delay as I'm supposed to. It'll loop through. And I'll check again once more if the switch is low. Likewise, go high or step through. I'll call the 250 millisecond delay, and I'll go through the generate DC or 100% duty cycle wave. Likewise, to the 0% duty cycle wave, I will just have a very simple step here. I'll set the motor to on, wait for the delay to occur 10 times, and check the status of the switch. If the switch was not pressed, I'll remain in the 100% duty cycle. Otherwise, I'll call my delay again and R jump all the way back up to this 0% duty cycle and fall through the loops again. To showcase this, I will kind of do a quick brief through of the assembly code here. So there's the org instruction showing where all of this happens in the ROM. I'll initialize a stack for my subroutines, set the directions of my input-output ports, initialize the outputs. Here I initialize the output LED to 0 instead of 1 because I would like to see the initial program loaded command. After every other time, however, when I come back to 0, the LED will be on to show that we have started into the 0 state. As can be seen, I load 10 into R25, call this delay 10 times. After stepping out when the push button is low, I call this inner loop subroutine. I'll flick over to that. Inner loop calls a 250 millisecond delay that also toggles the LEDs inside of it to save some instruction time. So going back up to the top. So the first inner loop occurs between 0 and 40. Then I load the two GPRs, 6 and 4, so off-on ratio. I do those two inner loops here and R jump to 40 if the pin is not pressed. Call the inner loop and step into 70. Otherwise, I turn the motor on as I did before in the 40. So the same process here. Inner loop once more before going into DC. In DC, I just set the port to 1. I will call the delay 10 times and check the status of the push button. Or I'll stay in DC. If the push button is pressed, I'll go through inner loop one more time before jumping all the way back up to the top here at motor control. I could also jump all the way to 0 here in that case. However, I felt like having more of a broad main label here. It'll still jump down the same way as if I called it to 0. so it won't accidentally step into delay when called, and inner loop is called in between loops as it should be. So with that, I'll go ahead and get into the hardware demonstration. With the O scope, you can visualize the duty cycle, frequency, period, and rise times. As I mentioned, the LED is off, showing that this is the first run through of this. So I'm going to go ahead and hit this button to enable the 40% duty cycle. That is on. As you can see, 40% at 250 Hertz as the program indicated. You get the nice square wave there. And the motor's spinning at a pretty slow pace and making a low hum. So I'll go ahead and step over into the 70%. The LED went off and back on, showing that we are now in the 70%. As can be seen, the motor is spinning a lot quicker, and the duty cycle is at 70% while maintaining the same frequency. Do this one more time. The motor is now having a higher pitch hum to it. The LED is on, indicating that we should be in the DC or 100% duty cycle. At 100% duty cycle, the duty cycle is actually inaccurate for reads, as is the frequency, because the frequency is not changing, so the signal is just held at that one value, or 5 volts. So if I step this down, we are now in the 0 state. The LED came on to show us that we are in the 0 state, and I can flick back through to the 40% duty cycle state. I can flick to the 70, and I can flick to the 100 again. Now back to off, and that's the full demonstration of Project 500.